So we've looked at hypothesis tests for population means and tests for population proportions. Now let's address tests for population variances. That is, we want to know if the population takes on a particular value of variance, sigma naught squared or sigma 0 squared. We've said before that variability is often a bad thing. High variability makes predicting behavior more difficult. For example, if we're production engineers at a factory, we need to have an understanding of the demand for the next time period to schedule raw materials and operators at the factory. Demand that is highly variable makes that difficult. Or if we're producing concrete beams for use in a highway construction project, variability in the strength of the resulting beams could be a problem, as we don't know what to expect from one beam to the next. So as you can imagine, answering hypotheses about variance is important. Much like the other two population parameters, we can have one and two-tail varieties of hypothesis tests. If we're testing whether or not the population variance is equal to some value, sigma naught squared, then we have strict equality in the null and strict inequality in the alternative. We could be testing greater than or equal to in the null and strictly less than in the alternative. Or we could be testing whether the population variance is less than or equal to sigma naught squared, or if it's strictly greater than. For example, we might want to know if the standard deviation of tensile strength of a particular concrete beam design is greater than 2,000 pounds per square inch. Then we'd have sigma squared greater than 2,000 squared in the alternative. The distribution of our test statistic is the chi-square distribution. Recall that n-1 times s squared divided by sigma squared follows a chi-square distribution with n-1 degrees of freedom. Therefore, the test statistic, chi-square naught, is n-1 times s squared divided by sigma naught squared. This test statistic looks a little bit different than the others, but it works similarly. When would we reject the null hypothesis? When the sample variance is significantly different than the hypothesized value. In this case, we determine how similar the sample and the hypothesized variances are with their ratio. If the ratio is a lot greater than 1, that suggests that the sample variance is a lot bigger than the hypothesized value. Therefore, we might reject the null. If the ratio is a lot less than 1, then we might conclude that the sample variance is a lot less than the hypothesized value. In either case, we might be concluding that the sample evidence is significantly different than the hypothesized variance. Recall that the chi-square distribution is truncated at 0, so we're not looking at the difference in variances, which could be negative. We're looking at the ratio, which can't be negative. And also recall that the shape of the chi-square distribution is a function of one parameter, the degrees of freedom. For this case, the degrees of freedom are n-1. Let's look at an example, answering the hypotheses with the critical value approach. Duff Brewery believes that filling beer cans with an average of 12 ounces isn't an issue. But the real issue is that the variability of the beer fill process is too high. The quality control engineer at Duff Brewery feels that an in-control process can't have a fill standard deviation of greater than 0.1 ounce. The engineer collects a sample of 20 beer cans and measures the fill amount in each of those cans. The mean fill is 11.95 ounces, and the standard deviation is 0.129 ounce. We want to be 95% confident in our result. The statement that we're focusing in on is greater than 0.1 ounce. A strictly greater than statement should be made in the alternative. H naught is that the variance is less than or equal to 0.1 squared, and the alternative hypothesis, H1, is that the variance is greater than 0.1 squared. The distribution of the test statistic is the chi-square distribution with degrees of freedom 20 minus 1, or 19, and this is a one-tail test in the upper tail. With 95% confidence, alpha is 0.05, and it's entirely in the upper tail. If we go down the degrees of freedom row to 19 and over to the column associated with 0.05 in the upper tail, we get a chi-square critical value of 30.1435. The test statistic is 20 minus 1 times 0.129 squared divided by 0.1 squared, which is 31.62. The test statistic lies beyond the critical value, out in the rejection region. We reject the null hypothesis and conclude that the variance is indeed greater than 0.1 squared. The quality control engineer at Duff Brewery may want to adjust the fill machine to produce a more desirable level of variability. And while we're at it, let's do an example problem with the p-value approach. An aircraft manufacturer needs to buy aluminum sheets whose standard deviation of thickness is less than 1/100th of an inch. Low variability among these aluminum sheets is very important for aircraft balancing. A random sample of 16 sheets from a potential supplier was collected, and the thickness of each sheet in the sample was measured. The standard deviation of the sample was found to be 0.0091 inch. The phrase to pay attention to is less than 1/100th of an inch. Less than doesn't imply an equality statement, so the alternative hypothesis is less than 0.01 squared. The null hypothesis must then be sigma squared is greater than or equal to 0.01 squared. The chi-square test statistic is n-1 times s squared divided by sigma naught squared, or 16 minus 1 times 0.0091 squared divided by 0.01 squared, or 12.42. We need the p-value associated with this test statistic. We know that this is a lower tail test, so all of the p-value must be located in the tail below 12.42. Recall that there's a different chi-square distribution for each degree of freedom, so finding the exact tail area associated with this test statistic is going to be difficult. We'll likely have to rely on a set of bounds for the p-value. Remember that the chi-square table always gives us upper tail values. So let's look at the row for degrees of freedom 15. We go across until we bound the value 12.42. We see 4.6, 5.23, 6.26, 7.26, and then a value of 8.55. Then the chi-square value jumps to 22.31. So the test statistic is bound between 8.55 and 22.31. Those bounds are associated with an upper tail area of 0.9 and 0.1, but we want the lower tail area. This must mean that the lower tail, the area below 12.42, must be bounded between 0.1, the complement of 0.9, and 0.9, the complement of 0.1. That is to say, the p-value is bigger than 0.1, and we can stop at that. We would never reject the null when a p-value is that big. We fail to reject the null, and therefore conclude that the standard deviation of aluminum sheet thickness is not less than 0.1 inch from the supplier. So there we have it. We've now learned about hypothesis testing for population variance when we're dealing with a single population. The chi-square distribution is a little bit trickier than the z or the t distributions, so make sure you do some examples of these kinds of problems. Otherwise, the process is the same idea for all the population parameters, mean, proportion, and variance. The critical value approach, the p-value approach. Everything works the same way, and we draw the same kinds of conclusions.